Swayam Prabha. Digital India. Educated India.
All right, let's get started. Welcome everybody. So our plan today is to talk some more about quantum algorithms, right? And in particular, we are going to see two algorithms, Simon's algorithm and Bernstein Vazirani. Okay, so let's jump right into it. So last time, as you remember, we've discussed the Deutsch and Deutsch-Jossa algorithms. All right, so Simon's algorithm is another really interesting algorithm that shows how this paradigm that we've been talking about of rotate, compute, rotate, how this can be used to give us something significant over randomized algorithms. So here's the problem. Okay, so given a function f such that f is 2 to 1, so this takes n bits to n bits. Okay, and f is 2 to 1 and it has the property that 2 points collide on the function value if and only if they are separated by some fixed value s, which is not equal to 0. Okay, so you can see that we are slightly warming up to this period finding type algorithm. Here the goal is to find s. So is the problem clear to everybody? Right, so we have 2 points that map to the same output point, right, if and only if they are separated by s. Okay, this is the problem, and the question is to find the value of s. So how much time do you think this should take on a classical computer? So it would take exponential time, right, because you need to actually hit 2 points so that they collide on the output value, and only that really can tell you the value of s. Well, as usual, we are going to do a lot better. It wouldn't be in this course otherwise. So once again we'll do it with a single query. Okay, so the query complexity that we'll get, oh, I'm sorry, not a single query, but n queries. This is still an exponential speed up. Okay, so let's see how. So this is the algorithm. Okay, so the algorithm once again, it follows this rough paradigm of applying Hadamard and then doing some computation and applying Hadamard again, but the details are actually quite different. So let's look at this algorithm. So first, you apply the Hadamard to the top n bits, you leave the bottom n bits unchanged. These are the ancillary bits at the bottom. Okay, then you pass it through this function oracle. So far so good. Note that at the bottom we did not apply a Hadamard. Okay, so the bottom bits that go into the function are zeros. So it's not minus or plus or something. So generally we have seen that we apply Hadamard also at the bottom and then this gives you phase kickback or something, but right now we are not doing that. So we just send it in as zeros. When the wires come out of the function, what we do is we actually measure the last n qubits first. Okay, so this is going to be our step 3. Our step 3 is to measure the last n qubits, and then we'll apply the Hadamard again on the top n qubits and then we'll measure. Okay, so for being explicit, I've written down the algorithm here. Okay, this is what we had in the picture. So first you prepare this superposition, we already saw that, this is the top n bits. Then you apply this function to it, right, with the ancillary 0 to the n. Now you measure the last n registers in the computational basis. So this is fairly different from what we have done before. Okay, you measure the last n registers, you discard this. So it might seem weird at the moment that you want to measure and then throw it away. You will see why we do that. Okay, so actually before we go into it, would anyone like to intuit why this kind of measurement might help us? Just stare at the problem definition, okay? Stare at the problem definition. So fx equal to fi if and only if y is x XOR s. Okay. Now, any thoughts on how this property is going to fit nicely with this step, this measure the last n registers and discard? Okay, I think it might be hard to think of at this moment. We'll go into it, and then after seeing the analysis, we'll come back and talk about this more. Okay, then having measured the last n registers and discarding it, then we'll again apply the Hadamard to the top n, and again we'll measure. Okay, and this essentially at this stage we get sort of one output. You'll see what that output means. It turns out that we need many outputs to solve the final problem. So we are going to repeat the above steps many times. So we'll have to discuss how many times to repeat it and so on. But this is the rough idea. Okay, so let's stare at this picture again. Okay, so try to memorize what's happening. Okay, so first you do the rotation on the top n. You don't do anything at the bottom. You push it through the function. Now you measure the last n, and then you apply Hadamard and measure the top n. This is the algorithm. Okay, so let's analyze it. So now what's going to happen? Well, the first Hadamard gives us our favorite superposition, right? So by now we are all experts at this. So this is just going to give me, this, right? So remember this we did not do anything. We didn't do anything to these last 10 bits. So this is all untouched. Now at the second step what we do is that we apply f, right? And as I already said, since we did not do anything to the bottom n bits, we are not going to get phase kickback or anything, rather we will just get fx in the last n registers. So once you apply f, then what you get is a summation over x fx. Everybody agree with this? Okay, this is just by definition, right? So remember we had fx XOR the ancillary values, and that is 0. So we just get this. Okay, now for simplicity I am going to ignore the normalization stuff. Okay, now the third step is the most interesting one. Okay, so measure the last n bits. Okay, say that I get some y. I get some value y. Now what happens is the interesting question. Okay, so my psi 3, right, it has collapsed the last n bits to some fixed value y. Now can you tell me what happens to the first n qubits? Anyone who has not seen this algorithm before? So please use the structure of the problem. Okay, so remember that fx1 is equal to fx2 if and only if x1 is x2 XOR s. And the hint is that now this is some y, right? I measured, it does not matter what value I got some value. The point is that this is going to collapse my first n qubits into x and x XOR, sorry, this is a typo over here. So, no, this was correct, I am sorry, this was correct. the point I was making is that it doesn't matter what y I got in the last n cube registers. The point is that this is now going to collapse the first n registers into two values that are separated by s. Does everyone agree? Yeah. So, what I will get here is something like this. Do you all agree? Okay, there will be a root 2 factor. As I said, I am not going to worry too much about these. Okay. So, what have I ended up with? I have ended up collapsing my first n registers into a superposition of two values that are separated by s. Okay, so this seems useful, right, because my goal is of course to find s. So now any ideas what what I am going to do now next? I mean the algorithm anyway we already discussed, right. So having measured the last n bits, I am just going to discard them and then I am going to apply the Hadamard on the top n and then I am going to measure again. So how should that help me? If I now apply the Hadamard, let us go to the next page. So now, right, if I apply the Hadamard on this, what will I get? So just based on our discussions before, won't I mean I will apply it linearly. So for this first state x, right, Hn of x is going to go to a summation over z, right, with minus 1 to the x dot z, right. So let's get that. So I am going to get a summation over z. Okay, so there is some Does everyone agree with this? This is what we have figured out before, right, that when I apply the Hadamard, then I on a particular value x, I get a summation over all z with minus 1 to the x inner product z in, as the coefficient and z as the state. Okay. So, summation over all z. So, this is exactly what I am going to get. And now of course, I am going to simplify this. Does everyone agree? So, this is just a simple algebraic manipulation, right. So, I have minus 1 to the x inner product z in both the terms. So, I will take that out. In one case, I will have 1 left, in the other case, I will have minus 1 to the s inner product z, correct? Everyone agrees with this? Okay. So, now the interesting thing that I am going to do is I am going to split this sum into z that are orthogonal to s and z that are not orthogonal to s. So, this is again it is just a rewriting, right. So, basically I can always take this summation over all z and split it into two partial sums of those z's that are orthogonal to S and those z's that are not orthogonal to S. Okay. And what we will see is that those z's that are not orthogonal to S, their coefficient will become 0. So, let us do that. Yeah. Can anyone explain how I got this? So, in the first case, when I have Z orthogonal to S, then I claim that I am going to get this term. Why is that? Exactly. So, because the inner product of S and Z becomes 0 in this case, I will get minus 1 to the 0, which is 1. So, I get something positive over here, right. In the other case where S is not orthogonal to Z, if the inner product is not 0, it is 1 because this is all mod 2, right. So, in that case I get 1 minus 1. So, this whole term will in fact go away, right. So, therefore, what have I ended up with? I have ended up with a superposition over all Z's that are orthogonal to S. So, there is some there is some amplitude that these different states have, these different Z's have. I claim it does not really matter, because when I measure this, I will get some Z which is orthogonal to S. And how many such Z's do I need? I need n of them, right, because I want to determine S, which is an n length vector. If I need n linearly independent Z's in order to fully recover the value of S just via Gaussian elimination. So, the final step of the algorithm is, as we have already discussed, so measure to get some Z that is orthogonal to S, do enough times, we will talk about this, to get n linearly independent Z, and this suffices to recover S. Everyone agrees? So, this is the algorithm. So, we have a little bit of details that we have not discussed. So, in particular we have not discussed how many times to repeat this, but before we go there, I would like to once again recap the idea of the algorithm. Okay. So, this was our algorithm. So, note that the first Hadamard, of course, created the superposition of inputs. Applying UF gave me a superposition of XFX. Okay. The key step here was that I am going to measure the last n qubits. What this allows me to do is it allows me to collapse to one fixed value of Fx. It does not matter what that value is. The point is that once I collapse to one fixed value of Fx, the input first n qubits, they get forced to become a superposition which is consistent with the Fx value, right. So, it becomes a superposition of some x and x XOR S by the promise of the problem, right. And then after that I am applying a Hadamard. What this is letting me do now is it is letting me split the resultant sum into terms that are orthogonal to S and not orthogonal to S, and what we analyzed was that the terms that are not orthogonal to S will have amplitude 0. Okay. So, this means that by applying the Hadamard again at this stage, right, at this stage, by applying the Hadamard again, I have forced the superposition to be restricted to vectors that are orthogonal to S. Okay, and then when I measure, it doesn't matter which vector I get, if it is orthogonal to S, that gives me some useful information about S. I need to make sure that I don't end up with linearly dependent vectors. So we can analyze that probability. So I won't talk about it in too much detail, but we will talk about it a little bit. So how many times do I need to repeat this? So order n, my claim is that order n repetitions give a constant probability of success. Okay, and essentially what I am interested in is analyzing that at a given iteration, what is the probability that I get a useful vector, right? So it turns out to be not very hard to analyze. So what is the probability that z1 to zk plus 1 are linearly independent? So when I sample the k plus 1th vector, what is the probability that I get something that is that is useful, so that such that all of them are linearly independent? So this I claim is 1 minus 2 to the k over 2 to the n minus 1, and this is just the probability that zk plus 1 is going to be in the span of the vectors that I have already seen. Does everyone agree? Okay, so this is just a simple probability analysis. So I need to now consider all the vectors, right? So probability of selecting an appropriate Zi in each iteration. This ends up being something like this. Okay, so you can work it out on your own. So just using the previous fact,